Hey everybody, here is a solution requested from the forums. Section 2.5, exercise 7. I'm just going to give a solution for part A. I'll leave part B as an exercise for you, but the model hopefully will give you a way to proceed to do 7B on your own. So the problem says this. In R2, let L be the line y equals mx, where m is non-zero. Find an expression for t of xy, where t is, part A says where t is the reflection of R2 about L, so across the line L. So let's just draw a quick picture, see what's going on. So here's R2. And then we've got some line, which goes through the origin and has some slope, y equals mx. The slope is m. And we're going to just reflect across this line. So points over here get reflected over there, and points over here get reflected over there, or rather vectors here get reflected to vectors there, and vectors here get reflected to vectors there, and so forth. Okay, so the question is to find an expression for t. So let's see if we can think about what's going on here. I've got this t really is some linear transformation from R2 into R2. And if we wanted to write an expression for txy, that would be sort of like knowing what it does to the standard basis. So that would be basically the same as looking at this diagram where we take R2 to R2 by t, but also you can represent R2 using the standard basis. So I'll say phi sub standard, and here phi sub standard. Well, that again just takes R2 down to R2 and R2 to R2, and then this matrix would be t with respect to the standard ordered basis for R2. And if we could work out this matrix, then that would be basically the same as being able to write down an expression for t in terms of what it does to x and y, expressing vectors in terms of the standard basis in R2. The problem is that I don't really know a nice formula. I don't know the matrix. In order to write down that matrix, I would need to know what happens to the standard basis. I would need to look at 1, 0, and 0, 1, and I would have to be able to describe where those go under the reflection. And if m is not 1, for instance, if it's not some really nice, easy slope to work with, then it's going to be a little bit difficult to express what happens to 1, 0, and 0, 1 under this reflection in general. However, here's the great idea and the insight in this problem. And if you think about the section that it's sitting in, section 2.5, this is the hint as to how one might think about this. If we chose a better basis that had something more to do with this geometric action, then we'd be able to write down the basis really nicely. And then the relationship between this matrix and the other matrix is just a change of basis matrix. So what do I mean by this? Let's think about a basis that actually has something to do with this line and this reflection. Well, what if I chose one of my vectors in R2, for instance, to be along this line? Well, what's a vector that points exactly along this line? I guess one easy one we could choose is just 1, m, right? If x is 1, then y is m times 1, so that would be a point on the line, and so I could just choose the vector that points from the origin to that point, 1m. Now this is really nice because when we reflect across the line, that vector doesn't move. Okay, so that's one vector. That's really nice. What about a second one? Well, remember, if we were pointing perpendicular to the line, this is supposed to be perpendicular, then the reflection is just going to be the exact opposite vector. So what's the vector that's perpendicular to the line y equals mx? Well, I could just take this vector 1m and sort of think about rotating it 90 degrees. So I would get negative m comma 1 as that vector. So this is great. So let's write that down. Let gamma be the set containing the vectors 1m and then negative M1. And I will not prove because I think it's pretty clear that this is a basis for R2. This is an ordered basis for R2. So now we can draw the same diagram for T. We can again talk about R2, T to R2, but now we're going to represent vectors with respect to this new basis gamma, phi with respect to this new basis gamma, and the matrix T with respect to gamma will be easy to write down. Let's think about how we should fill this in. Well, we'll just apply T to each of the vectors. T applied to 1m is going to be 1m, which as a linear combination of the vectors in gamma, that's just 1 times the first one plus none times the second one. And then when we try to apply T to the second vector, minus M1, well, this vector just gets reflected, so we should see exactly the opposite of negative M1. So I will write that. I will skip and even directly to the linear combination. I'll write that as well. 0 times 1m plus minus 1 times minus m1. It's the opposite of that basis vector. So that means that T with respect to gamma is equal to 1, 0, the coefficients from that first vector, and then 0, minus 1, the coefficients from that second vector. Great, so that's our T sub gamma. Now the question is, what is the relationship between the standard representation, or the matrix of T with respect to the standard ordered basis, and the matrix for T with respect to this new basis gamma? Well, if you'll remember, we can use a change of basis, or change of coordinates matrix. So if I took the identity transformation, I could talk about the identity with respect to gamma and then the standard ordered basis, or I could talk about the identity with respect to the standard ordered basis and then gamma. And of course, these two matrices should just be inverses of one another. So one of these is easier to write down than the other, and it's probably this one, because what I'm supposed to do here is apply the identity transformation to the vectors from gamma, and then write those as a linear combination of the standard ordered basis. Well, the identity applied to the first thing in gamma is just 1m, and in terms of the standard ordered basis, that has coefficients, that's right, 1 and then m. Now, if I apply the identity transformation to the second vector in gamma, negative m1, the identity does nothing to the vector, and then when I try to write that vector as a linear combination of the standard ordered basis, I get coefficients negative m1. So we could try to do the same thing for this matrix. If I want to apply the identity to standard ordered basis vectors, well then I'd have to try to write those as a linear combination of these vectors, and that's going to be super annoying. Or easier, I can just say that this matrix is the other one, the change of coordinates matrix in the other direction, it's inverse. And since this is a 2 by 2 matrix, I've got a pretty easy formula for writing down the inverse of a 2 by 2 matrix. It's 1 over the determinant, which in this case is 1 plus m squared times, I'm supposed to swap the positions of those ones, but they're both the same, so those stay the same. And then I change the sign of the other two entries. So this means that I have all the tools now to be able to write down this matrix for T with respect to the standard ordered basis, because I can write down T with respect to a better, nicer basis, and I know the change of coordinate matrices that are involved. So let's finally see all of that in action. Well, the matrix for T with respect to the standard ordered basis is equal to the identity. Actually, let me write it this way. It's equal to T with respect to gamma. And then on the right, I'm going to use the change of coordinates matrix that goes from the standard ordered basis into the gamma basis, so that then I can interact with something in terms of the gamma basis. And then I'm going to use the change of coordinates matrix that goes from the gamma basis back in terms of the standard ordered basis. Right, so let's do this calculation now. We said the identity with respect to gamma then standard, that's this 1 minus m, m1. 1 minus m, m1. Then T with respect to gamma, that was this really nice matrix. 1, 0, 0, minus 1. And then the identity with respect to the standard basis and then gamma, well, that was the one we computed by using the inverse. So that's times this constant 1 over 1 plus m squared times 1 m minus m then 1. And that's it. Let's just do this matrix multiplication. You can do it step by step. I'm going to skip ahead since I've done it in advance. And it's just matrix multiplication. It's just a calculation. So what we should end up with is 1 over 1 plus m squared out in front. We could multiply it inside, but I'm going to leave it outside for now. And then I'm going to get a 1 minus m squared, then the entry 2m, and then the entry 2m, and then the entry m squared minus 1, which is sort of nice and symmetric. Great. So that is the matrix for T with respect to the standard ordered basis, which means now if I think of T as being applied to an ordinary vector x, y, thinking of that in terms of the standard ordered basis, where I go x in the unit x direction and then y in the unit y direction, well, that's the same as multiplying a vector xy as a column vector by this matrix here. So I can write down the results pretty easily. If I were to multiply this matrix by an xy vector like that, then the first entry would be 1 minus m squared over 1 plus m squared. I should write that a little bigger. It would be 1 minus m squared over 1 plus m squared times x plus 2m over 1 plus m squared times y. That will be the first entry. Then the second entry will be 2m over 1 plus m squared times x plus m squared minus 1 over 1 plus m squared times y. There we have our expression for T in terms of what it does to an arbitrary pair of coordinates x, y. And just as a sort of sanity check to make sure that this is doing the kind of thing that we expect it to do, let's think about a simple case. Let's do a sanity check. When m equals 1, that would be a line of slope 1. That would be just this diagonal line. Well, we know what a reflection across the diagonal line does. That should exchange the roles of the x and the y. So let's see what our formula says. When m equals 1, this term would be 0. This term would be 1. So our first entry would be y. And for the second entry, well, that term would be 1. That term would be 0. So we just get an x. In other words, if m equals 1, then the reflection of the vector xy is the vector yx. That exactly is what we expect to happen. So there's our sanity check. It feels as though this is the right formula. Now let's just recognize that this is not an easy formula to come up with. If we just tried to start with an arbitrary vector, x, y, and describe how it gets reflected across this line, that is not an easy formula to derive. But when we use vectors that are actually connected to the geometry of the action, then we can use them, write down the matrix very easily. And the fact that the two matrix representations are related by a simple change of coordinates matrix makes all the difference. So hopefully that was helpful, and I will see you guys next class.